All right. Hello. My name is Joe Blazer. I am the head of marketing at A.Team and so excited to welcome you to our State of Prompt Engineering webinar. We're so excited to have you today. This webinar was honestly like way more popular than we ever anticipated. Over 1,000 of you registered. We have an amazing program for you here today. So before we get started, a little bit about A.Team. If you have not encountered A.Team before, because I know we have so many new folks joining our community here today. We are a network that brings together teams of the world's best product builders to build transformative products for everyone from startup companies to big enterprise organizations that are trying to push forward digital transformation efforts. So if you are a builder and you love building in new transformative technologies, check us out. There's some tabs in your webinar screen that you can use to explore us. And we would love to have you join us. A little bit of housekeeping as well. So Dan is going to stop and do Q&A throughout today's presentation. So get your questions in. There's a chat tab that a lot of you are using very actively right now. I absolutely love it. There's also a Q&A tab. So you can put questions for Dan in there. You can upvote them up and down. And then Dan's going to stop at a few different points and answer those questions for you. And finally, let's get to Dan. So Dan, I've known for a long time. Spoiler, he's a friend and also my brother-in-law, but one of the smartest people when it comes to AI that I've ever met. Dan is the AI lead at Ripplematch, a leading talent technology company. He is the author of the very popular open source framework Surveyi, and he has such a fantastic presentation for you here today. So without further ado, Dan, take it away.
Hey, everybody. Really awesome to be here today. Really excited to talk all about the state of prompt engineering, talk about large language models and how to integrate large language models into our products effectively. So my goal really with this seminar is to cut through some of the AI hype and really give people practical, useful advice about how to bring AI into their products from an engineering perspective, also a bit from a product perspective as well. So regardless of how technical your background is, I think there's going to be a little bit of something for everybody here in this presentation. So this presentation is called AI's Everywhere. Now let's make it useful. Large language models, what do they know? Do they know things? Let's find out. So quick little intro about me before we get started. Why I'm qualified to speak on the subject. So I have been building awesome products at awesome startups for nearly 10 years now. I'm an engineering manager. I've been leading our AI integration initiatives at Ripplematch. At Ripplematch, we've deployed several LLM integrations, and they're serving our thousands of daily users. And I'm also the author of Surveyi, which is an open source Python package for data modeling using large language models. And I'll talk a little bit more about all of that. I really threw this together and I reached out to Joe about doing this because one thing that I've realized over the past few months has been there's really just not a lot of good information about how to really integrate large language models into products. There's a lot of low quality information about prompt engineering, about engineering and building these into our systems in general. And getting that information requires a lot of immersion. It requires reading papers. It requires joining a lot of niche online communities. And so I really felt that there was a big need and a big hunger for this type of content that simplified some of these concepts and just opened the door for people who were interested, but didn't have that technical background yet. So that's really my goal here. And my goal is that everyone's going to leave with like a pretty good understanding and intuition about how to approach putting large language models into their products. So today's focus, we're going to do first a refresher on how large language models work. You may think you already know this, and some of you probably actually already do know everything that I'm going to say, but this is really important to keep front in mind as we get later. You can derive a lot of the best prompt engineering practices from some first principles that just come from understanding how large language models work at all. So just a quick refresher there is pretty important. We're going to talk about limitations and sharp edges. So basically, when it comes to integrating these systems, an important aspect of technical analysis is to try and understand the appropriate use of any technology. Large language models are very heavyweight solutions. So while they're pretty impressive, a lot of the times we might be able to solve the job with a simpler tool. And best engineering principles always say use the simplest tool for the job. Then we'll talk a bit about prompt engineering itself. So this has evidently become a pretty loaded term, as everyone who's told ChatGPT to pretend to be an excellent writer has now labeled themselves as a prompt engineer. But there's still many things that are important to understand. I'm going to walk everyone through some actual research, some papers on the topic, and hopefully everyone with a basic understanding of what the key ideas in prompt engineering are. Really, how do you build systems around large language models that make them scalable and effective and useful? Then we'll talk about some nitty-gritty technical integration strategies, how we can migrate some of these sharp edges we discussed previously. And we'll get a little into the technical side here, but I do think that this section has really important implications for how we design products when integrating with large language models too. And then finally, I'll gesture towards some more advanced techniques that you can consider once you've gotten all of the basics under your belt. So at the end of each of these sections, I'm going to pause and take some questions as well. I'm not going to have time probably for all questions, but I'm going to try to take a couple throughout, and then we'll leave some extra time at the end for some final Q&A as well. Okay. So before we dive into this, let's do a quick refresher on how large language models are trained and why this is important for us to understand. So the first step in the process is building what's called a base model. This first step is absurdly expensive and requires an absurd amount of data. The basic idea here is that you train a model on as much text as you possibly can find and and then train that model to predict the next token in a sequence. If you don't know a token, you can think of it as like a word. It's actually a little more specific than that. It's really, often sections of words, sometimes even letters, sometimes whole words, but you can just think about it as a word to simplify it in your heads. So this dynamic where the large transformer models go through a sequence, one word at a time, is what makes them what's called autoregressive models. Autoregressive is just a very fancy way of saying that I can't calculate a later point in a sequence without knowing all of the previous time steps in that sequence. All that really means is I've created a text prediction model, right? Like if I type into my text prediction model, my favorite animal is it'll give me some options with some probabilities associated with them. Maybe dog is number one. Maybe if you're a cat person, you think cat should be number one. But I have a text predictor. It's predicted the next token in the sequence of the text that I've given it. And because it's autoregressive, it has to go token by token. We can't skip ahead. We can't go back. We're literally computing token by token by token by token. So this process produces some really interesting side effects. So in order to get really accurate at making text predictions, we actually need to start learning patterns in that text. Geoffrey Hinton, who's a very, very famous computer scientist who's worked in the field, has said something to the effect of, if you had a perfect text predictor, it would know exactly what was going on inside of human beings' minds. And you can debate about if that's the only way to get a perfect text predictor. But the general idea is that in order to figure out when I say my favorite animal is blank, you have to start building statistical correlations with animals and how likely human beings are to like those animals. And those concepts, as these models get bigger and bigger, those encoded latent knowledge concepts get more and more complicated in the models. And so this can produce behavior that looks to us to be shockingly intelligent. I think there's a lot of debate about how intelligent truly these systems are, but I think there's no debate that they can appear intelligent. And the way that they appear intelligent is through the encoding of information that happens in the base model. Most of the intelligence is captured in this first phase of the process. But the base model is very difficult to use. So this phase of development is when the term prompt engineering first arose. So while those in the know were impressed with what these systems could do, some people as soon as GPT-2, a lot of people by GPT-3, they remained locked behind a steep learning curve that the average person wasn't going to be able to bypass. You had to structure your prompts in very, interesting and hacky ways to be able to get some of these sort of emergent behaviors out of the models themselves. So to remedy this, more recently, two steps were introduced. The first is instruction tuning. And instruction tuning models did what's called fine tuning in order to take the base model and refine its capabilities for human interaction. Essentially, examples of conversations between humans and a helpful AI assistant were provided, and much less data is actually used in the fine tuning step, but it allows the model to become better at performing a specific function. So in this case, like having a conversation with a person might be a specific function that you're fine tuning for. So what's important to note about, again, fine tuning is that you provide prompt completion pairs for it. So again, my prompt might be my favorite animal is, and the completion might be dog. In instruction tuning, the prompt is, hi, I'm a human and I really need help understanding ancient history. Can you tell me what year the pyramids were built? And the completion might be, hi, human, the pyramids were built in 3000 BC or whatever it is. Don't quote me on that. And then once we have our instruction tuned model, the final and most controversial step is to do what's called RLHF, reinforcement learning with human feedback, which creates a reward model as part of the AI pipeline. This basically amounts to human beings giving a thumbs up or a thumbs down as specific responses, and then using that data to further refine the model's output to be human legible. There's alternatives to RLHF in this last step, like Anthropic does something called RLAIF, but conceptually it's pretty similar. And there's a lot of debate around this step in the process. It's known that biases and other not so positive effects can be encoded into the model in this, but also it makes the models actually usable by the average person. I won't go into all of that. Just calling out that final step is a little controversial for some people. So one of the interesting trade-offs here is that as models go through the RLHF process, they actually experience a decrease in capabilities, but an increase in usability. So you can more frequently do stuff that's like, for instance, like zero-shot prompting. We'll talk about what that is with the RLHF models. But the side effect is that sometimes they get worse at stuff and they become less sort of intelligent in the process too. We'll talk about some examples of that. So this is a good place to pause for any questions that anyone has. So I'm going to pop over to the Q&A. Yeah, so there's a question in the chat about getting information from niche groups. So there's a bunch of different places that you can go online. There's a bunch of AI communities. There are the machine learning subreddit is honestly one of the best resources for learning anything that I've ever encountered. It's a very active group of researchers that are there. There's a number of newsletters and podcasts. Last Week in AI by Skynet Today is a fantastic one. Samuel Albany is an AI researcher who does a bunch of, goes over papers. Yannick Kilcher is another AI researcher who goes over papers. Those are some good entry point resources to start trying to build a model of the various ideas and research that's bouncing around in the very fast moving space. And yes, I can provide them in writing as well at the end of this. No, as far as like there's a question about, is the curve really linearly declining? No, it's not. And we'll go into some examples. That was purely for illustration purposes to just demonstrate the idea of the alignment tax. It's actually quite complicated. There's some things that, you would expect models to get better at in the process of RLHF, namely pleasing human beings. And there's things that they get worse at. So like an example that we'll talk about a little bit later in the presentation is that they get worse at picking random numbers. So it really depends on what you're measuring. It's not just like a straight linear relationship. It's pretty complicated. And there's a question, how big a data set should be for fine tuning? So we'll go over, and there's another question about recapping fine tuning. We'll go over fine tuning in more detail later, actually. But for fine tuning data sets, it can vary depending on what you're doing. My understanding is that the instruction fine-tuned data sets are in the hundreds of thousands of samples. In the order of magnitude of thousands of samples, you can sometimes get pretty great results from fine-tuning. So you're talking trillions of tokens for the base model, and then you're talking thousands, tens of thousands, hundreds of thousands of examples for fine-tuning, depending on how complicated the task that you're fine-tuning for is. Well, great. So there's a lot of great questions in the chat. I will come back to them if I have a chance, but for now, I want to keep going and make sure that we have time to get through everything that we're going to talk through. Okay. So next, I want to talk about limitations and sharp edges. So there are a lot with the large language models of today, and we need to design our product integrations cautiously to keep these in mind. So first and foremost, let's get the elephant out of the room. Today's large language models are slow and expensive relative to most ways an engineer could solve a given product problem. Before integrating an LLM, we should ask ourselves, can I solve this problem in a simpler way? It's crucial that we consider what LLMs are really good at and not good at. Otherwise, we'll just be giving our users a worse experience at greater cost to our businesses. We'll discuss more about how to mitigate this later on, but the burden of proof really needs to be on figuring out why this is a good reason to integrate an LLM into the product rather than the other way around. Most ideas for how to build LLMs into a product will be bad, but many will also be good. And we're here today to help be able to get everyone to tell the difference. So the next thing that's important to acknowledge is that as a highly stochastic and imperfect system, it's impossible to guarantee 100% accuracy in most cases with a large language model. And I'm not just talking about factual hallucinations, which I'm sure many people are familiar with. I'm talking about proper execution of a task when all of the proper information and instruction is provided to the model. With techniques we'll discuss later, appropriate task selection, we can get 80, 90, maybe even 99% of the accuracy, but it won't be perfect. And we need to prepare for the simple fact that there will be errors sometimes. And if something can't fail under any conditions, you probably don't want to use a large language model for it. Next, even though the state-of-the-art models are very impressive, they'll often struggle with multi-step tasks. So to be able to effectively use these models, we need to be able to break larger tasks down into smaller ones. But the trade-off is this will cause us a larger speed and price penalty if we're not very clever about how we do this. Another big area of struggle is that things that may seem simple to a human can be hard for LLMs. A classic example is reversing a string, or that they're very bad at math. The reason they're bad at string reversal actually has to do with tokenization. They don't actually, read individual letters most of the time, but instead read groupings of letters, which are the tokens. And the reason they're bad at math is multifold, but to come back to RLHF and the alignment tax concept for a second, it's shown that the reward function in RLHF can actually develop preferences for specific numbers. So an example of this is a non-RLHF model is pretty decent at actually doing random number sampling, while the RLHF models are not and show affinities for specific numbers in non-random ways. So very important to keep that in mind. Next up, you've probably seen headlines about bigger and bigger context windows. It is true that context windows are getting larger, but there are things about the transformer architecture itself which pose limitations that are going to be tough to overcome. Similarly, the more context window you use up, generally, the less good results one tends to get because you're making your task more complicated. Even for models with huge context windows, it's generally considered best practice to use as little of the window as you can get away with using. Claude 2, which came out recently, claims to buck this trend. I've not played with it myself, but it's likely that context windows are going to remain a fairly significant challenge for certain types of integrations into the future, especially if you care about high degrees of accuracy. And then finally, the companies have been struggling to keep up with demand. The OpenAI API routinely crashes due to heavy load. Companies like Anthropic require you to apply for API access. And this isn't a knock on them at all. What they're doing is really hard from an engineering perspective. But it will be the reality for a lot of people that, you need to get used to higher levels of unavailability than you would in most integrations. And these are all things that we can navigate. But I think before integrating large language models into our product, we should be a little scared. Good engineering principles say we should always use the simplest tool for the job. And these are very complicated tools. But now that I've done a little fear mongering, I want to then pivot and get into the good stuff. I'm going to stop for a second and answer a few questions in the chat. So there is a question about affordable using open source LLMs and fine tuning. For example, Falcon 7B, 40B, Llama 2 just came out as well. So speaking to the open source versus closed source, so for a lot of tasks, it might make sense to use an open source model and fine tune it. One advanced technique that I'm going to talk about later is using one of the more advanced large language models to build a synthetic prompt completion data set, which you can use for fine tuning for more simplistic models. This technique works really well. This is actually how models like Alpaca were able to achieve their strong results on certain benchmarks. Alpaca being Llama that was fine tuned with GPT-4 outputs. So that it can be a fantastic technique. I've not worked with Llama 2 yet. I will say that one thing that is notable about using some of the open source models is that there is overhead that you do need to take into consideration. They are a lot slower currently. So Falcon, for instance, is pretty notoriously slow, although it does have pretty high quality results. Llama 2 I've not tried yet. I'm hoping that it's a little bit faster. Hypothetically, if you can get an open source commercially licensed model, you can get it fine tuned, you can get it deployed, you can drive down cost very, very significantly relative to even using, say, like a GPT-3 fine tune, which would be another option to drive down cost. But it's hard because you're going to have to deploy these models, and that's a whole piece of your infrastructure that you're going to have to take into consideration. I think that the cloud tools for these open source models is going to get better over time. My own gut reaction to that question is that I'm definitely going to be investing time and trying to see how hard it is to deploy a Llama 2 fine tune, see how fast it is, benchmark it across all of the different types of benchmarks we have for our tasks. But I wouldn't be surprised if the best strategy is to not over invest in fine tuning open source models today, but instead wait maybe 6 months to a year, build the integration with a large language model or a fine-tuned cloud model today, because cloud service providers like AWS, Azure, GCP are probably going to offer really easy fine-tuning services for a lot of these open source models. So you may be just doing a bunch of work now that you later would have to undo. I think it's definitely worth looking into, but my gut is that it'll be easier to fine-tune open source models 6 months from now than it is today. And so it might be a lot of additional infrastructural work that isn't long-term beneficial. There's a question about my thoughts on ChatGPT's performance drift problem, and specifically if our RLHF model is hurting ChatGPT versus Anthropic's model. I don't know the specific paper in that's brought up in this particular comment, but I have seen papers. For instance, Anthropic published a paper about how they believe that their constitutional AI approach is better than RLHF, and they benchmarked it across a bunch of different areas like bias. And in theory, using AI to do the reinforcement learning process in a more first principles approach has a lot of appealing aspects to it. I suspect that probably the right answer at this moment in time is we don't know. You know, a lot of people are trying a lot of different things, and we'll have to wait and see as more and more research comes out. But I'd be very curious to read that paper, and if you have a link to it on Archive or wherever else, please throw it in the chat so I can take a look at it later. Great. So I'm going to move on for now. And there's lots of great questions again. I'm going to try to get to as many of them as I can, but I want to make sure that we don't get spend too long on any one section. Great. So now we're going to talk about prompt engineering. So the thing that's on everybody's mind. So prompt engineering has quickly become an extremely overloaded term on the internet since chatbot LLMs have started to take off. You've even seen some people like OpenAI's chief scientist, Ilya Sutskever, state that prompting is not something that we would expect to do in the future. So why bother learning prompt engineering? Case closed, right? And I'm going to make the argument that while prompt engineering is a term that's really hard to disambiguate, there exists a clear set of tools and ideas that are going to make our working with large language models much, much easier. Will this be a profession in 5 years? Uh, Probably not. But we can't neglect to learn to use the tool and then be frustrated when the tool doesn't do what we want. There are important things to know here, and some of these are intuitive, and some of them are very not intuitive. We can think of prompt engineering for our purposes as a set of meta strategies that help us get better results out of the model. These systems don't think the way a human does, and so we need to help them along a bit to get high quality results. So for a second, please forgive me while I engage in some strong anthropomorphization of these systems, just because I think human beings understand best by analogy. So importantly, for large language models, what you really need to understand is that computation is language, and language is computation. This is very important to keep in mind. There are no thoughts that the model has that are distinct from speech. Rather, speech is the same thing as thoughts. It's an autoregressive model. It computes a token at a time. This is really important to keep in mind. There's no magic that's happening in there's no like deeper layer of thought by default in these systems. We can architect them to have something that, approximates like thoughts, but by default, computation is language and language is computation. It's just very important to keep that in mind. So great. So the first thing that we're going to talk about is what's called in-context learning. Basically, what this means is that if a large language model is seeded with some text that contains a pattern or knowledge, the large language model is often capable of extracting that pattern. So a good example of this is what's called K-shot learning. The idea here is that we provide some examples of types of inputs and outputs the model might expect for a use case. For instance, we might be trying to extract some JSON format information from a large amount of text, very common task. So for these cases, we can write an example or two of extracted JSON, maybe paired with example inputs, maybe not. And then we send the text we want to be processed and ask the model to process it. And this was a necessary technique when folks were just using base models. But in many cases with instruction tuning and RLHF, it turned out that a lot of useful tasks can be done in what's called zero shot, which means that you don't provide any examples to the model. That being said, understanding and context learning is still important for many more complicated tasks. We may also want to seed the text we send to a model with useful information to help it accomplish its goals. If you've heard about vector databases, for instance, this is the role that they play in the stack. It's essentially figuring out what information we should seed our text with, and so the model can learn. This is called retrieval augmented generation. If you're familiar with recommended systems, there's the concept of like retrieval and ranking. Ostensibly, retrieval is basically the same process in this case. Like we want to get some records that we think might be useful, and then let the LLM decide, like, in its computation, how useful, how relevant are these records actually to the problem at hand. So one really good example of this, like just very trivial example, is that if you talk to GPT, it doesn't know what the current date is. That's because it has a training cutoff in 2021. So it can't tell you what the current date is. So you could easily seed your prompt with the current date. Then GPT will know what the current date is. Then when if a user asks what the current date, GPT will be able to answer because you've provided that information in the prompt. That's in context learning. And you often hide that from the user. So the user doesn't see all of the context window, but you're dedicating some of the context window to what you think will be useful to help solve the user's problem. Another distinction that's important to focus on here is latent knowledge versus learned knowledge. So latent knowledge is the knowledge that's encoded in the weights and the biases of the network itself that comes from the next word prediction training process. Learned knowledge is the extension of patterns and information that are in the context window itself. Latent knowledge is extremely buggy to rely on, and we'll get significantly more reliable results and less hallucinations if we try to make sure that we're always putting explicit learned knowledge into the system. So the trade-off here is, as I mentioned earlier, the more of the context window that is used, the more unstable our results will be. And the trick here is to figure out what knowledge is truly necessary to our problem and to only include that. Some other techniques that you may have heard of in terms of like what could probably qualify as in context learning are things like role play oriented prompting, like answer this question like you're an expert in mathematics. Since you're sort of teaching the model how to behave, you're trying to throw the model into some part of its distribution through your prompting. And I'll provide examples of more of these techniques, but one very important example of in-context learning is tool use. So LLMs can be trained to use tools via function calls. And what we mean by tool is essentially instructing the LLM to be able to call a function with some arguments. A remarkable characteristic of the training that's been done on these models is that they actually do a pretty good job of selecting the right tool for the job when presented with a few options, probably because of the amount of code that's in their training data. And we describe functions and their use case to the LLMs, and then it responds with a function call. You can extract arguments with a regex. You can do this with all large language models, including open source language models, although obviously the bigger ones, your GPTs and your Claudes, are much better at tool use. You could still fine tune for tool use with an open source model. This is also officially supported through OpenAI's API now, which makes it even easier to take advantage of if you're using them. Broadly, though, it is very easy to reproduce this behavior. This is really what makes these systems extremely powerful. This paper on the left here is not the first paper that described tool use by any means, but it was one that I thought was really cool. So Hugging Face is the easiest way to describe it for those who don't know. It's sort of like Git for models. Like you can host models on Hugging Face. It's a big machine learning community. And people host all types of models, image classification models, all types of use cases beyond large language models. And this was a paper demonstrating that you could use GPT in order to teach it how to do function calls, in order to delegate tasks to other machine learning models that were hosted on Hugging Face, which is obviously pretty powerful and pretty cool. So the next thing to talk about that you may have heard of before is something called chain of thought. So another important concept to understand is the reasoning capabilities of these models. It's probably their most remarkable property and the thing that opens up a wide variety of use cases. So chain of thought prompting is a technique which allows one to get more consistent, higher quality answers out of large language models by having them reason step by step. There were many different strategies to do this, which all kind of fall under the meta category of chain of thought. Early examples include like this one from Google Brain to the left here, which demonstrated using K-shot examples to activate reasoning abilities. But these days, most people zero shot chain of thought with you may have seen this, the classic let's think step by step by starting the AI assistant's prompt with that seed. You can get much, much higher quality results. And some of these are more or less default behaviors in chat models, hence ChatGPT's sometimes annoying levels of verbosity, but it's still really important to keep these things in mind for our own application. So that's going to bring us to a little pop quiz to see if you've been paying attention. Which of these prompts would we expect to perform the best? And which would we expect to perform the worst? So we're going to put up a poll, go vote, give you all a couple minutes to think about it, and then we'll talk it through. Give everyone another 15 seconds or so. All right, last chance to cast your vote. All right. Yeah, this was a tricky one. The answer is definitively System Prompt 2. And to understand why, we need to combine two ideas that we've talked about. So one is the autoregressive nature of these models, and secondly is chain of thought prompting. As we just talked about, we can improve the model's output accuracy for a problem by asking it to explain itself beforehand. There's a key here, though, that explanation needs to already be in the text for the explanation to affect the output. Remember, autoregressive models need to think token by token. So this means that it's impossible for a large language model to plan out what it's saying in advance. It can only plan one token at a time. This means that if the answer comes first, it is inherently causally disconnected from the explanation. The explanation is just a rationalization of the answer. It did not inform the actual answer. This is a very important thing to understand when working with these systems. They do not think like humans, and it's very easy to accidentally produce text that looks well-reasoned, but in actuality completely misses the mark. I think if there's one key takeaway from this today, I think this might be that key takeaway. Again, when we combine the chain of thought reasoning with the autoregressive nature of these models, it's clear that system prompt 2 will be our best prompt. System prompts 1 and 3 will probably be equally bad relative to system prompt 2. So I'm going to take a second now to pause for Q&A before moving forward. There's a question about open source models deployed and used in practice for production. Do I know any examples? I don't know any examples of open source models deployed in production currently. I'm sure people are trying. We're definitely going to try. We're doing research on it to see how quick we can get them. But for the reasons that I mentioned about, there's a lot of logistical difficulty in deploying these systems. There's a lot of infrastructural overhead to be able to run them, at production scale, and they're pretty slow compared to the enterprise alternatives. I'm not aware currently. I'm sure there are people out there, but I'm not personally aware of anyone who has productionized any of these models for a for-profit company. So there's a question about, can prompt engineering fix chatbot consistency with fine-tuning? Concerned about hallucinations. This is a great question. So I would say that the right answer is that we can decrease the amount of hallucinations significantly. The first technique that I would suggest doing is actually in-context learning and really taking advantage of in-context learning. Retrieval augmented generation is really going to be the technique that helps you reduce hallucinations at the greatest rate if you have a very good system in which you are drawing information from, a good retrieval system, essentially. Fine-tuning maybe can help depending on your use case, but fine-tuning does come with risks. You can, of course, like all machine learning models, you can overfit. I would say that it's hard to speak to it without knowing more of the specific use cases. Potentially, you could use fine-tuning in this way, but I would say in context learning, chain of thought, reasoning, the other prompt engineering techniques we're about to discuss, those will be more effective when it comes to dealing with hallucinations. Great. So I'm going to move on for now. And we got a few more prompt engineering topics to talk through. So first, self-consistency. So self-consistency is a set of techniques that look at the distribution of possible answers from a large language model, and then have some mechanism for selecting a frequently occurring answer among them. This is a really big tool in our pocket. So as I mentioned before, we can't guarantee consistent results from large language models. This is both because they're imperfect models, but also because of their stochastic, meaning random, essentially, nature. If we have temperature hyperparameters set above 0, then we might even get different answers to the same prompt if we run it a bunch of times. So self-consistency actually uses this as a feature, not a bug. We take advantage of that by sampling a distribution of possible answers. Then we look at the distribution of possible answers and make some sort of judgment about them. So I think the easiest way to think about self-consistency is majority vote. If the model is right 80% of the time for a given problem, Then if I sample an arbitrarily large number of prompt completion pairs for a given prompt and do a majority vote, then I should get the correct answer, even if any specific answer is wrong. So self-consistency is a really important technique. Of course, the trade-off with self-consistency is that this increases the speed and cost concerns as a factor of the number of answers from the model that you sample. So if you're using self-consistency, you probably want to parallelize a bunch of calls. If I'm sampling 100 answers, which might be what you need in some cases to really get strong signals from self-consistency, well, that's 100 calls to whatever language model I'm using. So it can get pretty expensive, but this is also a very, very powerful tool in the tool belt. Self-evaluation is the next thing I want to talk about. So self-evaluation is a technique that gets models to critique their own outputs. So a simple example here might be having the large language model generate an output and then feeding that output back in and asking the large language model to critique that output and look for errors. This is an extremely useful technique. Tree of Thoughts is a relatively recent paper that combines a few of the things that we've talked about to form a pretty sophisticated form of reconciliation across a space of possible answers. So the way that Tree of Thoughts works is by sampling a number of possible answers and then using self-evaluation with self-consistency to determine the plausibility of those answers. The plausible answers are then explored as part of a step-by-step reasoning process in a tree data structure, hence the name Tree of Thought. And so if any of those reasoning processes don't pan out and they reach an absurd conclusion, then the system will back out and then try to find another branch down the tree where it can follow the logic to a correct conclusion. This is a promising technique, similar to something called process supervision, and more so than overfitting on the specific strategy. I think it's just worth highlighting this is the type of idea to start thinking about when you explore how to structure your calls to the large language model. This is where the engineering aspect of it really comes in. Building a complex data structure that has self-consistency, self-evaluation built into the structure. That's how you can really start to get higher and higher and higher quality results out of these systems. So these 4 techniques that we've discussed in context learning, chain of thought, self-consistency, self-evaluation, they are really the building blocks of prompt engineering. We will talk about some more advanced techniques, but I think you can really decompose basically everything else as being built on the foundation of these ideas in one way or another. So next I want to talk about my framework, Surveyi, a little bit. So I think first it'll help to just explain what Surveyi does a little bit. So the idea that I became really interested in was I was very interested in the hallucination problem. And the idea that I became very fascinated with was, would it be possible to model distributionally the sets of answers that a large language model can give you, and then use that as some quantitative model to try to model real world phenomenon? So an example is, I had a bunch of AI agents. I had them read the top 10 news sites in the United States. I had them only, again, GPT's training data only goes up to 2021, so they had no knowledge of anything after 2021. I had them read news articles just from that month about the US election, and I was able to produce a graph that pretty closely mirrored the patterns of 538's election model, which is a best-in-class election model. There's some caveats here. I don't think that this is, useful for all use cases, and I think you have to interpret this data a little carefully. But the point here is that we can look at the relative changes in distribution among answers from a large language model and use those relative changes in distribution of answers to try to model something. And so talking about how Surveyi actually works, the user presents a hypothesis. So for instance, Democrats are favored to maintain control of the Senate in the 2022 November midterm election. Maybe you can also add some useful context as well. Then we create what's called a survey, which consists of a bunch of AI agents. They use a relevant tool. So for instance, search Google for news between some dates and with the query 2022 Senate midterm election predictions. And the LLM figures out what tool to use, and it figures out what arguments to use that tool with. Then this is one of the interesting things about Surveyi. This isn't really prompt engineering. This is more data science, but we only pass a subset of articles to each agent, and that's to give each agent a unique sort of perspective on the topic. Each agent then uses self-critique, self-evaluation. So each agent constructs an argument in favor of the hypothesis using the data and an argument against the hypothesis using the data. Then each agent looks at both arguments and evaluates which one it believes is better. Then the agents, we do self-consistency. So at the end, the agents vote on whether the hypothesis seems more likely to be true or false, given the available evidence. And then we output the percentage of agents that support the hypothesis. And that's how we end up with a graph like this. So this uses all four techniques we discussed. It uses in-context learning in the relevant tool use, and it uses in-context learning in passing the articles into each agent, into their context window, so that they can be used as evidence. It uses chain of thought in the actual reasoning and the construction of the arguments themselves. It uses self-evaluation in the selection of the superior argument. And it uses self-consistency in the voting system in order to try to output a final output. I'm going to pause for questions one more time here, and then we have one more section to get through. So there's a question about why do long models with long context windows tend to bias towards the start and the end of the window? So this one has a lot of upvotes. I want to acknowledge it. I actually don't know the answer to this. I was unaware that that was the case, and it's non-obvious to me why they would bias towards the start of the window. It does, biasing towards the end of the window, I think maybe makes a little bit more sense. But if you think about how the attention mechanism works, I don't know that I would intuitively expect this to be the case. So I actually don't know the answer. And if anyone knows, definitely write it in the chat. How much tuning is too much before hitting catastrophic forgetting? This is not a question you can give a definitive answer to. You're just going to have to see. In the next section, we'll talk about some best practices, but you just have to have benchmarks, and your benchmarks need to be robust for any system that you're trying to automate. And ultimately, you'll be able to tell. What I recommend doing is having various goalposts in your fine-tuning process. So instead of fine-tuning from scratch from the beginning, instead, fine-tune on this much data, this many epochs of training, this much data, this many epochs of training, and then you can benchmark it over time. In general, with machine learning, what you tend to see is what's called overfitting if you train for too long, where it'll get maybe marginally better at the training data loss, but it'll get worse actually at the validation loss. It's very, very hard to predict where that peak of that maximum minima of validation loss is going to be without just running it. There's tools like weights and biases that might help you visualize it, but at the end of the day, you're just going to have to experiment. Great. So moving on to the next section. Hyperparameters. So I just want to talk a little bit about hyperparameters. So the reason that they're called hyperparameters is because the internal state of the model is what's referred to as parameters. So for neural networks, those parameters are weights and biases. So hyperparameters are the parameters that exist above the parameters of the model itself. So these tweakable parameters can affect the behavior of the model in various ways. I'm only going to touch on two of them. There's more of them. First is temperature. Temperature is essentially the model's willingness to sample a token other than the most likely next token. So for instance, coming back to our first example of our prompt is, I like to pet and the next most likely token is dog. If the temperature is 0, then the completion will always be dog. However, if the temperature is some non-zero value, then it might be some other token that's somewhat likely, let's say cat. There's another hyperparameter called top P that I won't go into, but it's similar to temperature insofar as you tweak it in order to change the likelihood that you'll select tokens that are not the top tokens in some way, shape, or form. You can kind of think of tweaking temperature as like tweaking the randomness of the model, and it's really only recommended that you tweak temperature or top P, but not both. And then max tokens to sample is the maximum number of tokens in the response. It's useful to set as low as reasonable, and there's a few reasons for this. Low values can help the model have consistent low cardinality responses if you're treating the large language model as like a classifier, for instance. And lower max tokens to sample also result in faster response times as well. Great. So now we're on to our last section, which is integration strategies. So let's revisit our sharp edges from earlier. 1, the LLMs today are slow and expensive. 2, you cannot guarantee accuracy of task completion in 100% of cases with a large language model. 3, large language models struggle with complex multi-step tasks. 4, there's broad categories of simple tasks that large language models struggle with. 5, context windows represent a challenge for large amounts of text. And 6, these companies are struggling to keep up with demand. So first, do the science first. Before integration begins, validate your use case with your data. If you are trying to automate something quantitative, then you should be able to determine the accuracy of your methodology against quantitative metrics. So for instance, at Ripplematch, one thing that we use large language models for is document extraction. So you can compare manually a curated sample in your examples against the results of your document extraction. If you're doing something qualitative, then create a large distribution of responses and have internal team members validate at least hundreds of these for quality. Ideally, have multiple people evaluate the same responses to increase the probability of catching errors. Do not assume that a large language model can do the task you want it to do until you have validated it at scale with actual data. I can't stress that enough. And having those data benchmarks, those Jupyter notebooks, that'll come in handy later too. Once we have it working with a large language model, we want to trim down, fine tune, use a smaller model. We have our benchmarks ready to go. And so we can validate against our benchmarks. So no replacement for doing the science. Next, parallelization is key. Since these models are slow, parallelization is key to making many of these multi-step strategies work effectively. So there are often clever ways to parallelize components of your problem, aggregate those components, and then further process them as you need. So for instance, we talked about how having a smaller max token to sample is going to lead to faster responses from the large language models. So if I'm doing document extraction, let's say I want to build this big JSON object that's got like 40 different fields. If speed is more important to me than cost on this particular task, I could parallelize that. I could say, I'm going to decrease my max token to samples per call, but I'm going to parallelize, 5 extracted keys at a time. Parallelize those calls, get them back. It'll be way faster. Be more expensive, but it'll be way faster. And then make sure to implement exponential backoffs due to both rate limits. It's hard not to run into the rate limits with the cloud-based solutions. And the fact that you should expect more API downtime than you're used to with a third-party integration. Next, break your task into parts. So you will get better results from a few perspectives by breaking your task into smaller chunks. Higher parallelizability is one benefit. Faster responses is another benefit. Higher accuracy is another benefit. Do all the steps require an LLM? It's a great question. Maybe you only need an LLM for one key piece of the logic, but you can make everything else a much faster, much simpler system. For instance, some people, when they're doing, so if you're doing a classic retrieve and rank system, like what recommender systems do, in order to build the information that you want to use for in-context learning, some people like to actually use the large language model for ranking. But maybe that's overkill. Maybe you can use a very classical system for retrieval and ranking. You don't even need to use a vector database, nothing complicated. Just very simple system for your use case. And you just use the LLM for whatever the step that you need the more complicated functionality is. Can you get away with using the LLM only for a subtask? And can you cache results? It's another big piece of it. Any step that you can cache results, you want to. Next, always have a backup plan. So remembering that we're going to have a potentially high number of API failures, potential slowness, and impossible to fully guarantee accuracy, we should build LLMs into parts of our business that have higher ambiguity tolerances. And this is a really important lesson for product and business leaders as well. For instance, a good place to start integrating would be automating internal business practices with high levels of redundancy, somewhere you can keep a human in the loop. These systems are not ready to drive themselves in most cases yet. You really want a human being double checking the work. And when presenting the experience to the user, stream results to the user, and then have a backup plan if results aren't ready in some amount of time. So strategy that we've taken, we stream results to the user, but if results aren't ready in a few seconds, we'll default to a slightly inferior user experience, and which would have been our old user experience before we integrated with large language models. And if we can guarantee uptime for 90% of users and they'll get that great experience, that's better. But it's just a logistical reality that we can't guarantee that experience for 100% of users today. And we have to build that into our thought process and integration. And then finally, I want to talk about some advanced techniques. So my suggestion would strongly be to build your prototype, your MVP, with a large language model before you do anything open source, a cloud-based large language model, before you do anything open source, before you do any fine-tuning. Because like most product builds, you don't know if it's going to be a good product until you put it in front of users. So if you've validated that the large language model works for your use case, it works for your product, you may be able to further improve performance and cost through fine-tuning and language model cascades. So we've discussed the fine-tuning in the context of instruction tuning. Many labs let you fine-tune models yourself, open source, can fine-tune it on your own hardware if you want. It's been found that for specific tasks, fine-tuned models can perform as well or even sometimes better than the large generalizable models. And these fine-tuned models can often be shrunk in size significantly, which makes them faster and cheaper to run. So a good strategy is prove product market fit with an LLM integration and then explore fine-tuning to save costs down the line. This is what we did at Ripplematch. We made sure that we could build what we wanted to build. We made sure that it worked well, and then we were able to cut back costs significantly through fine-tuning. And then a language model cascade is a set of logic that routes different queries or tasks to different language models based on model capabilities. There's different ways to do this. You could have a model that just like detects which model to route to. So the idea here is that, maybe I know that there's 60% of user queries I can answer with this really, really cheap model. So I'm just going to do that. Maybe I can even answer 20% of queries without ever going to an LLM. So I'm just going to do that. And then only the 20% that I don't know how to answer with the cheaper solutions, I'll use the expensive large language model for. And yeah, so that's it. We're getting close on time, but want to spend some time trying to answer any questions in the chat. So there's a question about what are my thoughts around privacy concerns when sending business data for in-context prompts. Yeah, so this is a great question. I think ultimately this is going to be for every company's compliance to figure out. For us, so OpenAI and Anthropic are GDPR compliant. They claim that they do not store any of the data that's sent over the API. So if you're sending information over the API, according to what they say, you should be okay that data is ephemeral. Now, there's some data that there's tighter restrictions around in general. I know healthcare is a great example. I can't speak to every single example about what's okay to send or not to send. If OpenAI are not storing that data, you have a secure connection over the API to OpenAI. In theory, that data is as secure as going over any other third-party integration. It's not less secure than any other third-party integration. If you are using the chat interface, however, they do store your prompts, they do store your data. So I would strongly discourage putting anything that you have any privacy concerns about actually talking to ChatGPT. If you're going over the API, it's a slightly different story. There's a question about what the best training courses for prompt engineering are. I think this is really honest. This is why I wanted to do this in the first place. I honestly think most of the resources that are out there are pretty poor, to be honest. I'm going to share a list of resources. I'm sure I'll be able to email the RSVPs. I'll put together a nice list of what I've used to get up to speed on it. But they're not really courses. It's more immersing yourself in the people who are active in the field and are learning. It's really new. A lot of this stuff is new, and it really changes really, really quickly. It's been generally my experience that most people who put themselves forward as prompt engineering educators on social media, a lot of them don't really know what they're talking about. So I'll provide a bunch of high quality resources that you can start to use, but it's not really a course. It's unfortunately the best way to learn right now is immersion and experimentation, which works well for some people. So do I think big data solutions can achieve better results, or at least more cost-effective results than LLMs for common usages that GPT is utilized for today? Yes, yeah, I definitely do. I definitely do. I think that I think there's a lot of nuance here. Again, you want to use the simplest tool for the job, and you want to use the tool that you are empowered to use as a company. Some companies have really great data. They have really great data pipelines. They're able to train their own custom models, and that can work really well. I don't think it would be smart if you have a model that you've trained yourself on your data to just swap it out for GPT. GPT might be worse. You have to benchmark it and test those benchmarks. When it comes to fine tuning, however, it is true that to fine tune a model for language-based tasks, so the thing that language models would be good at, you need much, much less data. I am sort of suspect, and this is, looking at my crystal ball here, that what we're going to see is a real explosion in the fine-tuning ecosystem, making it really easy to fine-tune open source and closed source models really quickly and effectively, because you really just need like orders of magnitude less data than you would need to train any other type of model. So I suspect a lot of what we use large language models, meaning the biggest version of these models, the instruction tuned RLHF, ChatGPT, GPT-4s of the world. I suspect a lot of those use cases will be carved out by a marketplace that emerges around smaller fine-tuned models. But I do think there's a lot of advantages of fine-tuning even 7 billion parameter models over trying to make a model yourself. Great. So I think we're at time. So going to wrap it up now. Again, I'm going to send out an email to everyone. If I couldn't get to your question, apologies. Lots of great questions in the chat. Really love all of the engagement. Feel free to reach out to me on LinkedIn. You'll have my email after this. Feel free to shoot me an email. I'm happy to answer any questions that you all have. So really, thanks for joining me today. I had a really great time, and hopefully everyone leaves with a little bit more understanding and intuition for how you can actually really apply these systems into your product.
All right, amazing. Hopefully you guys can hear me now. I just unplugged my tricky podcast microphone. Dan, thank you so much. That was an amazing presentation. Super engaged chat. I can see everyone really loved it. As Dan said, we're going to follow up with all those resources, also our upcoming events. We hope you guys continue to come back, engage with us virtually, in person in New York and other cities that we're in. We just had an amazing hackathon in Chicago this past weekend. Let us know where you are, where you'd like to see us take this show on the road. But this was just absolutely fantastic and so great to be with all of you. Dan, thank you again. And you can all expect to hear from us with tons of great follow-up content tomorrow. All right, have a great one.